We're going to understand the meaning of a second derivative. I mentioned that to you in class yesterday, and it's going to be fairly straightforward what a second derivative is. We're going to understand the meaning of both the first and second derivatives in connection with a position function. We've done position functions before, and we're going to be able to apply these derivatives to problem solving. All right, that's kind of the whole goal of math. Math is not just about trying to solve equations and that kind of thing. It's supposed to be applicable. It's supposed to be relevant to your everyday existence. So that's relevant. That's what we're going to be trying to do. Show how it can be relevant to your everyday existence. So higher order derivative. Let's start with that. The derivative of function is denoted by f prime of x. You know that. If the derivative of the f prime of x is taken, then we're going to refer to that as the second derivative of f. And it's denoted by f double prime of x. So you can see where I'm pointing to on the screen there. So the f prime of x is your first derivative. If you take a derivative of the derivative, then it's referred to as a second derivative and refer to that as double prime of x, f double prime of x. If you're using a Leibniz notation, which you're familiar with, we talk about dy dx. If it's the first derivative, that's the first derivative, dy dx. Then the second derivative is referred to as d2y over dx squared. So if you see d2y over dx squared, we're referring to the second derivative of the function. So you take the first derivative and find the derivative of that. That's your second derivative. That's your f double prime of x, or your d2y dx squared. Okay, so let's take the first example of that. We should get through this fairly quickly, by the way, and give you enough time to get to the homework. But let's keep going. Let's take the first and second derivative of the following function. Very simple. The first function, or the actual function, is the minus x cubed plus 2x squared plus 9x. That's your original function. So just using the derivative of polynomial approach, the solution to that would be the f prime, so the first derivative, is a minus 3x squared plus 4x plus 9. Nothing new there. We've done this a million times. Well, maybe not a million, but we've done it enough times. And my second derivative is the derivative of the first derivative. So that's just minus 6x plus 4. As simple as that, right? So original function, first derivative, second derivative. Let's take one a little bit more challenging. What's the first and second derivative of the following? So this is a rational function. So yes, we're going to use the rational function tool, which is the quotient rule or quotient law. So the dy dx of that is the derivative of the top multiplied by the underived bottom. So 1 times 2x minus 3 minus the derivative of the bottom, which is 2, times underived top, so minus 2x, and that's over the denominator squared. Again, that's just simply using the derivative rules. So that's your first derivative, using the quotient law. Now, for me to do the second derivative, I'm going to simplify this, right, the dy dx. So if I were to take the 2x and minus the 2x, I'm going to end up with just simply 3. And for me to do the second derivative, and there's a minus in the front of that, right? I mean, hopefully everybody appreciates that. Minus 3, that is. I'm going to write it a different way because it's going to be easier for me to do the derivative again if it looks almost like it's a polynomial, right? We can just use the simple polynomial laws to derive this first derivative. So my second derivative looks like this. My d2y dx squared would be the minus 2 times the minus 3, which is positive 6, 2x minus 3 to the minus 3, and then the chain law kicks in, times the derivative of the inside function, which is just simply 2, and therefore it would look like that. 12, I expect you to simplify these all the time, by the way. So that's why I'm going through the process of making sure I'm giving you the simplest way to write a function. I don't expect you to leave it like this or leave it like that. I expect you to reduce it down to its lowest terms. Let me get my pen out here. So this would not be complete. This answer here would not be complete. That's incomplete. I expect you to go further than that. All right, same thing here. This would also be incomplete until you get to this stage. It's not done. So this answer is what I would really be looking for, as well as this answer. right? So get your algebra skills in order so that you can carry it through to the next stage like the way I did it, all right? Okay, so when do I need the second derivative? What's the point of getting a second derivative? Well, let's apply that to velocity and acceleration. And I'm going to show you a Khan Academy video a little later on, which relates to all of this. But let me introduce it to you first. If you have a function s of t, right? Now remember we did those position functions before. So s of t represents the distance of an object. What position does that object have from some place, some start position? So this is what the s of t function represents, just where you are, what position you are, or what distance you are from some fixed point. The s of t, we know, is the velocity of the object in motion. So when that velocity is positive, you're moving in one particular direction. You're moving away from the object if it's positive. If it's negative, you're moving towards the start position. All right, so that's what velocity represents. It's the first derivative. The second derivative is the acceleration of the object. So not how fast you're going, but how is your velocity changing itself, right? So if you're on the highway, consider yourself to be on the highway. You're moving along, you're looking at the speedometer. Speedometer says you're doing, let's say you're doing the legal limit, which is what you're supposed to do, by the way, 100 kilometers per hour. Well, that's your velocity, right? That's how your position on the highway is changing over time. So remember, 100 kilometers per hour means every hour you've moved 100 kilometers. So that's what velocity represents. If you look at your speedometer, that speed or that velocity is not changing, right? You're doing the legal limit, you're just sticking at that particular position. But what if you see the speedometer changing? What if you see you going from 100 to 110 to 120? You're not supposed to do that. Let me just say that. Let's say you do because you want to overtake somebody. Some of you I know have licenses already. So if you need to do that, you're going to see the speedometer change, right? So instead of you going at 100 kilometers per hour, you've accelerated, you've changed your position, you've changed your velocity, which is already a measure of your rate of change of position. You're also seeing how that velocity is changing by way of acceleration. So if you change from 1 to 110, it means that your velocity has increased by 10 kilometers per hour. And that's what your second derivative is really measuring. How is your velocity changing? Of course, you can also decelerate, you can slow down. And both of those can be measured by the second derivative. If the acceleration is positive, then it probably means, and we're going to get in more detail of this, so it's not always that a negative acceleration means that you are in fact slowing down. That's not always the case, and we'll see why that is in a minute. But the acceleration is how are you changing your velocity? So that speedometer, how is that speedometer changing? Is that speedometer just sticking at one speed, or is it changing? Are you going down to 60 sometimes? Are you going up to 120 sometimes? That's what acceleration is measuring. How is that changing? Okay, so before I share the following statements with you, I'm going to share a Khan Academy video with you. So I'm actually going to stop the recording for a bit. Okay, so let's see if we can describe what's going on in each situation now. Let us say that we had at 2 seconds, let's see if you can follow what Salman Khan was saying in his video a few minutes ago. At 2 seconds, the following things were happening. You took your 2 seconds, put it into your position function, and it said you were at 4 centimeters. Put that 2 seconds into your velocity function. It says you are going at 2 centimeters per second. Put that 2 seconds into the acceleration, that's your second derivative function. And it says that your acceleration at that point was 1 centimeter per second per second. You notice it says 1 centimeter second squared. It means the same thing. That's the way we normally say 1 centimeter per second per second. What that means is that every second your velocity is increasing by 1 centimeter per second. That's why we say 1 centimeter per second, or 1 centimeter squared. So that's the way it's normally said. So I'll do the first one for you. And then let's see if you can help me to get the others after that. So 2 seconds in the velocity, sorry, in the position function, same 2 seconds. So we're trying to figure out what's happening at 2 seconds. 2 seconds in the velocity function, 2 seconds in the acceleration function. Well, here's the answer for the first one. You're above the start. So I want you to think of it. He was using left and right. I'm going to use above and below. So that's why I wanted to do the first one with you. I'm above the start because it says 4 centimeters. So I'm above the start. If it was negative, then I'd be below the start. But 4 centimeters means I'm 4 centimeters above my starting position. At the same 2 seconds, I'm moving upward. How do I know I'm moving upward? Because it says that my velocity is 2 centimeters per second. So once this is positive, it means that I'm going upward. If it was negative, it would mean I'm going in the opposite direction because velocity not just has, and you learn this when you're doing vectors, not just has magnitude, it also has direction. So this velocity is 2 centimeters per second going upward. And this says I'm speeding up. And the 1 centimeter per second, along with the velocity at 2 centimeters per second, is how I know that I'm speeding up. He went into great depth to describe how you know you're speeding up at any particular point in time. So I've done the first one for you, right? I'm above the start. I'm moving upward. So let me use my stylus here a little bit. So let's say that I'm using a vertical line, right? So consider this to be 0. That's my starting position. So at 2 seconds, I'm somewhere, let's say my particle is somewhere up here above the start, and I'm actually moving in this direction, right? That's what is happening in this case. All right, so I'm going to click on this. And let's see if you can figure out what's happening in the second scenario. So S of 2 is minus 4 centimeters. S prime of 2 is 9 centimeters per second. That's positive. S double prime of 2 is minus 2 centimeters per second, and that's negative. So can anybody, using what I just did for the first one and listening carefully to what Can just said, can you fill in all the blanks? Am I above the start or below the start? Am I moving upward or downward? Am I speeding up or am I slowing down? Okay, so Carly says I'm below the start. Okay, that's a good start. What else? Am I moving upward or downward? Moving upward and slowing down, Adam says. You're below the start, moving upward and speeding down. Okay. So we don't talk about speeding up. You either speeding up or slowing down. Let's use that Sarah way of saying it. Okay. So let's not say speeding down. So let's say speeding up or speeding down. Okay. All right. So let's see if you're all right. Well, there you go. Below the start, you're moving upward, but you're slowing down. And the reason you're slowing down is because these two things are going in the opposite direction. So what's happening is that you are somewhere down here. This is where you are, but you're going in this direction. But what's happening is that, sorry, you're going upward because that's what the positive says. But what's happening is that your acceleration means it's pulling you back, right? So it's slowing you down. It's actually making you go in. It's actually pulling that 9 centimeters downward, and that's why you're slowing down. Okay. All right. Let's try 2 more scenarios. Let's see if you're really as sharp as you started off looking like you were. Okay. Look at those at the 2 second mark, right? Above the start, below the start, moving upward, moving downward, slowing up, slowing down, speeding up. What's going on for this one? Help me out, folks. All right. I need to know some details. So Adam says above the start, moving downward and speeding up. All right. Above, down, and slowing. So not quite the same answer from Sarah and Adam. Above the start, moving downwards and speeding up. Okay, Anika sounds like she's kind of in the Adam in the Adam column there on the Adam train. All right. Well, what do other people think? Javier says above the start, moving down and speeding up. Interesting. Does anybody have another answer? Right? Any other answers apart from those answers? Okay. All right. So let me give you the official version of this. You're actually slowing down, right? You have to consider again the fact that these two things are opposite direction. Let me show you again what this is going to look like. So again, I'm going to use my little 0. So that's the starting position. So you're 8 centimeters away somewhere up here, right? It says you're moving in this direction. but you are actually adding to your downward velocity, and that means that you're slowing down. Okay, so that's kind of what's happening here. So some of you got that right. It's about to start moving down and slowing down. Okay, great. Yes, Tash, great. Okay, so one more. Let's see if everybody can nail this one, right? Hopefully everybody can understand the difference between when you're slowing down and speeding up, when you're moving upward, moving downward, when you're about to start, below the start. Okay, last one. This is at the 2-second mark, and those are the variables. Tell me what's happening this time. What's going on here? Below, you're going down, speeding up, Sarah says. Okay, what do other people think? Below the start, moving downwards and speeding up. Interesting. Adam and Anika seem to be on the same page. What do other people think? I'd love to hear from other people. I mean, I kind of tend to hear from some of the same people on time. Ariana is agreeing with them. Anybody else? Come on, folks. There's 28 of you in the class, and I'm only seeing from, okay, actually, okay. So it sounds like everybody's in agreement with that one. So below the start, moving downward and speeding up. So what's happening is that you are now below. Is there any way for me to erase this? Maybe not. Anyway, so you're all right. So let's just put it that way. Happy as agreeing. So excellent. Good stuff, folks. Let me move on. So let's go to problem C now. Object is moving along a number line according to the position function. And now we're going to get specific because I'm going to give you an actual equation. And hopefully you can see that clearly enough. So the position function is given by a p of t being 5t squared minus 1/3 t to the power of 3. T is in seconds, and the position, is in centimeters. So what's the object's position at 3 seconds? Let me ask you that question. All right, so go ahead and do your calculation. Where is the object at 3 seconds? Right, based on the information that you have, based on the function that you have, do what you need to do and tell me where this object is at the 3-second mark. Moving along a number line, right? And it give you a function, and they give you a time, and they want to know where is this object. Come on, folks, get your calculators out, do the work. Do what you need to do. And give me some answers. Don't let me bring the wheel out now. All right? I'm going to threaten you with the wheel. The wheel is only a mouse click away. Okay, Stephen is saying 36. Jordan, everybody's coming in with the 36. Yeah, you know what? Tom is at 36 as well. Okay, look at the thread of the wheel. Actually, you know what? I'm still going to start the wheel because I think I'd love to get some involvement from a lot of people, and there are some people who are very forthright, and I really love that. But let me see if I can just get my little wheel here. 1 second, please. Open my MCV. Where am I? Q2. That's these guys. Yeah, there we go. Perfect. Okay, I got my wheel ready. Got my wheel ready to go. And let's see if the answer for that first one is right. So I'm just going to put the 3 directly into the function, and it's 30 centimeters on the right. So it's kind of important to also note where you are in relation to your starting position, right? If the way that we're doing this is considered to be a number line, then you're either going to be on the right or the left of the number line, depending on whether the position is a positive or a negative. Okay, so 36 is absolutely right. And please don't forget your units whenever you're answering any question to do with speed or position or acceleration. Units are actually quite important. Okay, next question. What is the velocity of the object at that time? Okay, so over to you, right? And I'd like everybody to work it out, but I'm going to go spin my wheel in the meantime. And it may be one of you who is always ready with an answer, or maybe somebody else. I have my name ready to go. Okay, so I have a name ready, but I'd like everybody, don't put any answers in the chat yet, right? Just go ahead and calculate it. Do what you think you need to do to calculate it. And also, let me just give you a little word of advice. I also need to know what direction we're going in, right? So not only give me velocity in terms of a number, I'm reminding that velocity has a magnitude and a direction. So I'm not going to give you any clues as to how to do this. I'm just saying that your answer should involve both. So what's your actual velocity, what's the magnitude of the velocity at that time, 3-second mark that is, and in what direction are you moving? Okay? All right, so I'll give you another 30 seconds to get your answer. And then I'm going to ask one of you, and I have a name already, to give me your answer. Okay? If there's anybody who isn't sure what to do, then please ask, because when I call on you, I don't want to hear silence. If there's, I was still finishing up my test when the video was playing, and so I'm catching up. No problem, Adam. And I will have the recording of the class so that you can always check with that later on. No problem. Okay. And yeah, so I was about to say, if there's anybody who isn't sure about what they need to be doing, please ask so that if I call on you in a few minutes, few seconds really, because we don't have a lot of time here, then you will have an idea of what you should be doing. Is there anybody who wants a little bit of a push start, a little bit of a prompt, or is everybody fairly confident about what you're doing? Okay, I don't see any response to that question. So I'm gonna go over to Kashaf. Kashaf, are you with us? Can I have a push start? Okay, sure, Fernando. So, okay, so Kashaf, let me get your answer, and then we're gonna. First of all, let's hear what Kashaf's answer is, and then I'm gonna sort of work with Fernando after that. Go ahead, please. Oh, okay, no problem at all. No problem at all. So, how do we get velocity? Let's ask both of you that question. What would give us velocity? We don't have a velocity equation, do we? They gave us a position equation. So what do you think we need to do to figure out velocity? And I'm posing that question to Kashafa and to Fernando. What can we do to get started with the velocity? Any thoughts on how we could do that? Fernando, what do you think? I'm starting off with a position function, but what I'm interested in is velocity. That's really what I'm trying to get here. Absolutely, Kashaf. Do you see what Kashaf just said there, Fernando? You see her answer? Perfect. Because remember that the derivative of a position function is a velocity function. So what I want you both to do now, and Kashaf, I'm going to come back to you on this, is to find that derivative of the position function. You have the equation there. And then use that to figure out where you are at the 3-second mark. Kashaf, does that kind of point you in the right direction? Good. Okay, go. All right, so now that I've talked, now that I've said what it is I wanted to work on it, that doesn't mean the rest of you should be slacking off. So those who weren't sure what to do, you should be working this out for yourself right now as well. Kashaf and Fernando were the ones who were bold enough to step up and say, I need a little help. And that's that I admire. What I don't like is when people sit there and do nothing. Okay. All right. So we'll give her a chance. And Fernando, you should be trying as well. I appreciate that you raised the concern and hopefully I've addressed it. And if you're still not sure, then please let me know. Okay. You have some units for that? And you can tell me what direction we're going in. Are we going to the right or to the left? Seconds? Fernando, can you help her out with the units on this? Okay. All right. Okay. So let's see what we have here. So we took, first of all, the derivative of the function. All right. Okay. So Alexander is saying centimeters. Not for velocity, Alexander. Centimeters per second. Okay. So what we're going to do is we're going to take that and put that into the, first of all, there's a derivative function, 10t minus t squared. And that's hopefully everybody is okay with that. And we're going to put that same 3 seconds into that velocity function now, because this first derivative of the position function is our velocity function. And it works out to 20 centimeters, 21, as you said, as Kashaf correctly said, 21 centimeters per second moving on the right. So you're moving in a rightward direction. Okay, so Kashaf, well done. Okay, so everybody understand what we're doing so far? Is there anybody who's still sure? Because I don't mind, as I said, I keep repeating this. You let me know when I need to stop, rewind, and come again. Okay, so let me know. All right, so let me move on to the next question. So first one is that you're 36 centimeters away from the center, right? Let's say it's a number line. So you're on the right side of the number line, and you're moving at 21 centimeters per second towards the right. So that's where you are at the 3-second mark. You're 36 centimeters away, moving at a speed of 21 centimeters, going further to the right. Okay. What is the acceleration at that point? Okay, so everybody, go back to your calculators, go back to your pen and paper. I'm going to take Kashaf out. She did a good job. And I'm going to get somebody else to give me that answer. Now, if you're not sure, tell me now, please. Tell me right now that you need some help to get that answer. And I already have a name ready to go for that. Don't know how to do that, Adam said. Okay, Kushi. Kushi, you saying the same thing as Adam, I'm assuming. Kushi, you want, okay, can I also have some help? Absolutely. Okay, so what we're saying is, good, good. Thanks for the questions. So, and this is what I want, folks. This is exactly what I want, right? Tell me when you're not sure. So, what is the acceleration at that time? So, we're still talking about at the 3-second mark. Now, remember, we started off with a position function, right? We took the first derivative of that. It is a second derivative, Adam. You're quite right, right? So, I took the first derivative of that function, and it worked out to be this function here, 10t minus t squared. That is my velocity function. The first derivative of the position is velocity. And look at what Adam just said. If I now want to move to acceleration, I'm going to have to now take the second derivative of that function, which is the derivative of the position of the velocity function. So I'm going to take my velocity function, which we got as 10t minus t squared, take that derivative and put that time into that. So Zach, Anika, Kushi, does that help you, or do you want to say some more about that? I mean, I can, but does that help you all out? Anika says yes. Okay. How about Zach, and how about Kushi? Does that help you out as well? Okay, a little. Okay. So remember, just follow the sequence here, Zach. That's what I had done, but I was guessing. Okay. The sequence is the first, the original function, which is the one I'm pointing to now, right? That just tells you where you are. That's it. Okay, Zach? Position is how far am I away? In fact, let me put that on a number line on here. All right. So put that up here. So let's say the number line, that's your 0 on the number line. The first thing we did is we found where you were at 3 seconds, and that was 36 centimeters away. So that's where you are. So let's consider that the thing that we're trying to, that's a 3 there, folks. Ah, geez, it looks ugly. But anyway, that's a 3 there. So anyway, that's your third. That's where you are. But what's happening is that it says you're moving this way at a rate of 21 centimeters per second. But it's also saying that that speed is changing. And the way you can figure out how it's changing is to go to your second derivative. So take the second derivative. So take a derivative of this derivative, Zach, right? That derivative is the first derivative, and it only gives you velocity. But if I take the second derivative, that's going to give you acceleration. Okay, Zach? Does that kind of make it a little bit more clear? Just a little bit? Okay, good. All right. So I have a name. I'll announce the name in a minute, but I want you all, if there's anybody else who still isn't sure, please let me know, and I can try to rephrase that for you. All right? Okay, so another couple of seconds, and then I'm going to be asking for that answer. And with the proper units. Remember, we talked about the proper units for that. If you're not sure about the units, we can help you out with that. But at least do the calculation. Okay, hold on to that, Tumblr. We're gonna get to you. We're gonna get to that. All right. So Anika, turns out you're the one that we chose. So do you have an answer ready for us now? If you need some more time, let me know. Okay, so you're saying it's 4 centimeters per second squared. All right, so let's have a look at that. And you're speeding up to the right. So, and you notice that I have seconds squared. So Tomalaya, just answer your question. Yes, it is centimeters per second squared. Because what it is centimeters per second per second. So what's happening is that you're adding to your 21 centimeters per second at the rate of 4 centimeters per second is really what we're saying. So Nika, well done. Right? Just the only thing I would say is that you should say speeding up to the right. So you're going faster and faster. This is actually when you're speeding up, right? You're actually speeding up because you're adding to your velocity moving to the right. Okay? Forgot about that part. Okay. All right. That's okay. That's okay. Do we have to write left or right? You should. You should. Right? You should. Well, you could actually write whether it's well, not so much whether it's left or right, but you should actually say whether it's speeding up or slowing down. When you talk about acceleration, that's one of the things you should also try to mention. Okay. All right. Good stuff. Good stuff. Now, let me try to put this in some perspective with the same kind of diagrams that we had with Mr. Salman Khan. All right. When will the object be moving forward? Now, the red line, let me label them. The red line, I put it over here. One second. Hopefully you can see the colors from where you are. The red line, hold on, let me move this down. Okay, so the red, I can't color code it. Okay. Well, I can, but let's just go with all of them being well, my writing is going to be in the same color. The red is your actual position. Right? The blue is your velocity. And the green is your acceleration. Okay. I think I did too much here. I didn't expect to. Geez. Okay. When will the object be moving forward? Now I've given you the velocity function, which is the blue line here. And I didn't expect to actually, I revealed too much. Let me see if I can go back here a bit, although I've already given away part of this. All right. So when will the object be moving forward? Based on the graphs that you see here now, right? When is the object moving forward? Can you answer that question by just looking at the graphs? Is that possible? It is possible, actually. If you look at hopefully you can read your x-axis fairly easily. When is this object moving forward? Stephen says from 0 to 10. How does Stephen know that? I'm going to agree with Stephen, by the way, right? How do we know that it's moving forward? What is it that makes you know it's moving forward? Well, the velocity. And what about the velocity, Alexander? The blue function is above the x-axis. That's correct. And the other thing is that you can look at the red line itself and can see where the red line is moving up, right? That means the object is moving forward, right? So just looking at the red line, it actually tells you that the object is moving forward, right? Once it's going up. But the other thing is, yes, if this thing, which is the position function, right, has a positive slope, then the thing that gives you the slope, which is the blue line, is also going to be positive. So it's positive anywhere from 0 to 10. No, it's more positive. It has a steeper slope here than it does as you get closer to the top. And that's why you'll notice that this thing, although it's still positive, is now starting to go down, right? So it does mean that the slope, although it's still positive, is kind of decreasing, okay? All right, so the red line is telling you that it is moving forward, and anywhere from 0 to 10 is moving forward. And that's what this is saying. So velocity, so the v of t function is this function, t into t minus 10. So velocity is 0 at t equals 0 and at t equals 10. So velocity is positive, and it means the object is moving forward between 0 and 10 seconds. So I've given it away before I expected to give it away, but there you go. Okay? All right. So far, hopefully, so good. When will the object be speeding up? No, you have to try to remember what Khan was trying to teach you before. And that is, you have to compare when your velocity and your acceleration are both negative or both positive, right? So, can you look at this graph and figure that out, right? Can you see where the remember that, and I gave it a color code for the previous one. In fact, I'll write it here again. So the red line, okay, let me see if I can do this again. The red is position. The blue is velocity. And the green is my acceleration. I'll just put ACC. All right. So Ariana says from 11 onwards, the blue function is above the x-axis. All right, let me just see if I can get a sense of what everybody is saying here. All right, the blue function above the x-axis, Taj, okay. Depends on what direction we're referencing, doesn't it? Not really. Okay. It's we can talk about it speeding up. Did I just go to problem C by accident? Can I go back here? Oh, okay, good. I didn't give it away yet. No, we can talk about it speeding up in either direction. So in other words, yes, you can talk about speeding up in the upper direction or speeding up in the lower direction. All I'm asking right now is though, when is it speeding up? That's really all I'm asking. When is it speeding up? So can you answer that question based on just the graphs that you're looking at? All right. So a lot of different answers here. I see one answer that says from minus infinity to infinity. So everywhere is what Stephen is thinking. Taj is thinking from 0 to 5 and from 10 to infinity. And Tomalaya is suggesting the same thing. All right, so let's see. A lot of people. So there seems to be so from 5. Sarah is saying depends on what direction. No, direction is not, like I said before. Direction is not the issue here because you can be speeding up in either direction. Right, speeding up to the right, speeding up to the left. So let's think this through now. Ashvan and a bunch of people seem to be thinking 0 to 5 and 10 to infinity. And I'm going to show you how we can confirm that right now. So we're looking for where both the green line, right, and the blue line have the same sign, right? Have the same sign. Doesn't mean that you have to be positive to be speeding up, right? Acceleration does not have to be positive to be speeding up. If you're both negative, both meaning the green line and the blue line are both negative, or the blue line and the green line are both positive. So let's just agree on something here. And by the way, the domain of the function is that x has to be greater than 0, right? So we're not considering anything to the left of 0, right? Mentioned that in Khan's video earlier on. So let's talk about when you're at 0 itself, right? Starting off at 0. As I move to the right, at the 1 second mark, let's use the 1 second mark for as an example. At the 1 second mark, are we speeding up or are we slowing down? Look at the graphs and see if you can tell me at the 1 second mark, are they speeding up or slowing down? Right at the 1 second mark, just at that particular point, at the 1 second mark, right? And then we can answer the question as to why the answer is speeding up or slowing down. At the 1 second mark, are they speeding up or slowing down at the 1 second mark? We'll talk about why later on. Okay, Sarah is saying slowing down. Okay, here's the thing, Sarah. Can you agree with me that at the 1 second mark, the velocity is in fact positive? Right? I know it's going down. I get that. I understand that. But can we agree that it's positive at the 1 second mark? Right? The green line is in the positive zone. And can we also agree that the blue line is also in the on the positive side because that's their velocity function. So if that's the case, then it means that you are speeding up. I know that the acceleration line is going down. I get that. But at that point, your acceleration is positive. So can we agree that anywhere between 0 and 5, not including at 5 and not including at 0, but anywhere between those two, between 0 and 5, both the blue line and the green line are positive? That's part of where you're speeding up, right? Does everybody follow that? And I'm going to, as I said, reference that video. I'm going to put that video into the, I'm going to make sure I put it, I'm going to put it into the calendar as well to make it easy for you to find it, but it's also going to be in the math video library. Okay, now what happens after 5 is that although my velocity is still positive, my acceleration now went negative. So that section doesn't qualify anymore. So anywhere between 5 and 10 doesn't qualify anymore. But look what happens after 10. After 10, so here I'm at the 10-second mark now. After 10, both my velocity function and my acceleration function are now below the x-axis. So anywhere from here onwards, I'm speeding up. I am speeding up in the negative direction. Let me just be clear on that, right? I'm speeding up in negative direction because of the fact that they're both negative. Okay, so there's the difference right there. So from 0 to 10, object speeding up when both velocity, so speeding up from the first 5 seconds and then again after 10 seconds. So there's your answer right there.